Hey folks, this is Captain Jones here to talk to you about the rest of the LC3 instructions, or at least most of them. Our objectives today are to describe the term instruction set architecture and actually give you the instruction set architecture for the LC3. We're going to define not quite all of them, but 8 of the remaining 10 instructions. And the reason is because we got 2 that we're going to save for Unit 3. Part of that is going to be to make sure that we define opcode and we describe the LC3's 5, this should say 6 addressing modes. I want to take some time in this lesson to also compare and contrast the terms computer architecture with computer organization. And lastly, introduce 2 terms and kind of talk a little bit about them, which are a RISC and CISC, or reduced instruction set, complex instruction set computers. Let's get started. On the left here is our pyramid of abstraction, which hopefully is familiar to you. Recall that we're going to take, this kind of shows us how we take simple logic gates, we can build them all the way up into awesome computers that implement software languages that let us solve tough problems. And it's sort of the organization and the architecture levels here where we're going to spend most of our time in this course. The instruction set architecture is effectively synonymous with architecture here on this level of the pyramid. And there are 3 big components to that. The instructions that our computer is able to execute, the registers that it has that we can reference, as well as how large and what type of memory is available to us in the computer. So let's look at these 3 things together. By way of comparison, I want to sort of bring your attention to the little man computer. Believe it or not, this device has an instruction set architecture, its registers are effectively 1, right? The little accumulator inside the middle of this calculator. Memory-wise, it's pretty limited, but there's something there. We have 100 mailboxes that can each hold a 3 decimal digit value. And when we were looking at this earlier, we saw that there are 10 instructions available to us that the little man computer can execute. And so, although very simple, this is a complete instruction set architecture that defines the little man computer. So let's look at the same thing for the LC3. We're already familiar a little bit with the registers in the LC3. We know that there are 8 of them, numbered R0 through R7. And we've already seen some instructions that let us, do useful things with the values in those registers, add them together or load them from a place in memory. The LC3 has a memory which is 2 to the 16th spaces tall, so a little over 65,000 memory spaces. Each of those spaces are at least 16 bits wide. So a 16-bit piece of data can occupy each memory space. Each space in memory is given the term a word. So if we talk about one word, we're talking about a chunk of information with 16 bits wide. And in the LC3, memory is said to be word addressable. That means, if you can see here on this graphic, that when I increment my memory address by 1, I move from one word to the next. So I can address at, the smallest thing I can address in my memory is 1 word, 16 bits. There are some computers that have a word length of 32 bits, so twice as wide, and yet their memory is byte addressable, meaning memory address 0 would refer to these 8 bits, memory address 1 would refer to the next 8 bits, and that's useful in some circumstances. But on the LC3, the word length to 16 bits, memory is word addressable. And this is the complete set of LC3 instructions. We're already familiar with a couple of these, right? A lesson or 2 ago, we saw our add instruction that came in 2 flavors, our and instruction that came in 2 flavors. We looked at the branch instruction. We took a look at the load instruction and the trap instruction. And so our goal today is to make you familiar with all the rest of these instructions. And so this reference is taken directly from Chapter 5. I really encourage you to print that out and keep it somewhere handy, because it's going to be a useful reference throughout the rest of this course. All right, so our instructions, recall that they can be sort of sorted into 3 categories: operate, data movement, and control. In the intro lesson, we looked at these 5, and an add, which are operating instructions, load, which is a data movement instruction, and branch and trap, which were control instructions. Our goal today is to introduce you to these 8 instructions, not LEA, which stands for load effective address, LDI, which is load indirect, LDR, which is load register, a store equivalent of each of the load instructions, and the jump instruction. The last 2 instructions in the LC3 ISA are JSR, which stands for Jump Service Routine, and RTI, Return from Interrupt. We'll talk about those in Unit 3. So those will be the 2 that we reserve a little later. It's at this point in time that I'm going to let you know the text does a wonderful job of explaining these instructions to you, and I will not belabor them. I did earlier for the first 5 because I wanted someone to walk you through what those instructions are and how they look, but hopefully at this point you're familiar with what these instructions kind of look like, what sorts of things they're capable of, and I'm going to tell you, dive into chapter 5, dive into Appendix A, figure out what the rest of these 8 instructions do. I think maybe we'll do an in-class exercise to help sink those in, but I think there's more than enough material in the textbook for you to become comfortable with those. For the rest of this video, I want to discuss just a couple of kind of peripheral issues that either help inform your understanding of these instructions or that sort of come out of our study of these instructions. So the first is related to something called addressing modes. The addressing mode for a specific instruction basically answers the question, where's the data that we're operating on? So, the data there might be a value in the instruction that we're using, there might be a value in the register somewhere, there might be a value in memory, and how we figure out what that is what determines our addressing mode. So in the LC3, the book says 5. I say there are 6 addressing modes, and you'll see why, and I'll show you why in a sec. Which I sort of group into effectively 2 categories. One is if the value or the piece of data we're looking for is sort of local, which to me means it's either in the instruction or it can be computed directly from like the processor elements, versus if the value we're looking for is somewhere in memory. All right? So if the value is local, there are the book will say there are two addressing modes: immediate and register, also known as register direct. So an immediate value means the piece of data we're looking for is in the instruction itself. And examples here, this add instruction, when the LC3 goes to execute this instruction, it's going to add the value 6 to register 5. It's going to find the value 6 literally in the register, right? Bits 4 through 0 are going to specify that number. The register addressing mode says we're going to find the value we want in some register. So again, we can use the same instruction for this. When the LC3 executes this instruction, it's going to get the value that it needs out of register 5, and then add it to the immediate or literal value 6 that's in the instruction. So this one kind of piece of code is an example of both of these addressing modes. Right? The addressing mode that I think the book doesn't quite recognize is this one here, PC relative, which it does talk about, but it talks about it in terms of the load instruction. So let me put this one on hold here. We'll jump down here. We got a couple of different ways we can find values in memory. The book will tell you the very first one is PC relative, meaning we're going to take some value in the instruction, we're going to add it to the program counter, and then that forms the address of the piece of data that we want. So an example of that would be our load instruction here that we looked at a few lessons ago. I'd formulate this. This is the result of adding the program counter to some value in memory, but this is sort of a relative value that I get from the instruction and the program counter. And I'm going to go to this address in memory and get the value and store it in register R0. So the book would say that's PC relative. I say there are 6 addressing modes. So to go back to this one up here, because we can use the same format basically when we're executing, for instance, a branch instruction. I'm going to add some value to the program counter to become my new program counter. I kind of feel like it's different because in this case, we're not taking the result of this and reaching into memory to get a value. It itself is the value that we're using to update the program counter. So maybe the author and I kind of differ a little bit on that. The last 2 addressing modes down here are indirect and base plus offset, or which is sometimes called indexed. So indirect, this is kind of a weird one. So I would encourage you to spend a little bit of time with this to make sure you understand what's going on here. But for my load indirect and also my store indirect instruction would be another one example of this. What I'm going to do is take some value in the instruction, add it to the program counter, and treat that like an address in memory. The value in memory that I get is the address, again, of the next place in memory where I'm going to look. And it's at that location that I get the data value that I load into R0. All right. Let's see. The book explains this. Where did it go? Oh, here. Okay. Okay, so I'd spend a little bit of time with 5.3.2. This is an example here that shows you, what this looks like, and I'm not gonna use the exact values because I'm coming up with this a little bit on the fly, but we're gonna say that basically if I got memory here, um, if my PC plus offset, let's just be super simple here. Let's say it has the value 1. Okay, that's pointing to this spot in memory. Let's say the spot in memory at memory location 1 has the value 3. Okay, so what the load indirect or store indirect instructions are going to do is calculate this offset, look in memory, that we're going to treat that value like another address. And then whatever's in memory location 3 in this case, if it's a load indirect, that value would go into the register. If it's a store indirect instruction, then I'm putting a value here. And you'll see some examples as the course progresses of where this is really useful. And then the very last addressing mode here you can see base plus offset. What I'm going to do is take a value in a register, add to it some offset value that's in the instruction, and then treat that like an address. Then I'm going to get something out of memory. So in this example here, load register R0, R1, decimal 0 means I'm going to take, in this case, 0. I'm going to add it to whatever values in R1. So R1 effectively has the address of the data that I want. That piece of data is going to get loaded into R0. There are about as many addressing modes as you can think of, because there's so many different ways. If you look at the format column, so many different ways we could shift and add or combine values in the instruction register versus instructions in our register file to get at values in memory that would give different computers different capabilities. So these are not the only 6. There's lots more, and unfortunately there's not a standardized kind of way of naming these. So that's why some of these have sort of like a slash, that kind of 2 names, right? PC relative slash PC plus offset are kind of 2 different names for what we're going to treat as the same thing. All right, next I want to talk about architecture for versus organization. So I've got my pyramid of abstraction on the left here, and now that we know about our instruction set architecture, we can kind of define the delineation between these 2 levels a little more clearly. The architecture is my instruction set architecture, right? It's got discusses my registers, my memory, what instructions are in my computer, and this is what's known as sort of the model, the block diagram, if you will, of my computer. It's also sometimes called the programmer's view of the computer, because it should have only the information that someone needs to be able to write programs for the computer without any implementation details. The organization, on the other hand, is kind of exemplified by our data path here. This is an actual instantiation of the architecture and its full implementation details, meaning how these circuits are connected. And so this is the actual hardware that we're using to implement the architecture. It's sometimes also called the microarchitecture. And we won't. Well, actually, we will a little bit later. We'll see how it's totally possible for one architecture, so one instruction set architecture, to be implemented in multiple different ways. We'll see actually in Unit 5 how we can actually implement the LC3 architecture in a slightly different organization, a slightly different fashion that gets us some benefits. All right, lastly, I want to talk about reduced instruction set computers versus complex instruction set computers. So instruction set, this is referring again to the instruction set architecture. Kind of the basic dichotomy is that in a RISC or reduced instruction set computer, the prevailing philosophy is I'm going to make this computer simple, kind of like a Swiss Army knife. It's going to do a couple of useful things, and that will hopefully keep the design very simple and let me make the computer really fast. The complex instruction set computers take a slightly different philosophy. They say, well, no, we're going to try to make these computers really fast by designing them to have many, many, many different types of instructions that do a whole bunch of different stuff. And the idea is, in that style of computer, I can take my high-level programs and since the instruction set of the computer is much more capable, I can use fewer instructions to implement that program. So an example of this here, the LC3 computer we're going to play around with is very definitely a RISC style computer. The kind of classic CISC computer is the x86, which is probably the CPU that's in your laptop right now. So you can see here a couple of different ways in which these two compare. The LC3 has 15 instructions, whereas the x86 has, by some counts at least, over 1,000. The LC3 has, the book says 5 addressing modes, and the x86 we have more than 24 different ways we can address data. The LC3 has instructions that are of a fixed length, or 4 bytes long, whereas in the x86, the length of instruction varies from as little as 1 byte all the way up to 15 bytes. Also notably different between these two are that in the LC3, the positioning of our operands is very consistent. You might recall from the first lesson on our introduction to the instructions that the destination register occupies like the same spot in all of our instructions that sort of write to a register. And that's opposed to the x86 where, you know, to allow these instructions to kind of vary in length, operands kind of move around. And what that effectively means is that the LC3 in general we might expect to have a higher clock speed. It's a simpler, you know, design. It's going to have less circuitry, and therefore we can run the clock a little faster. This being an ideal world, right? Clearly, the LC3 is not a production level device. The x86 has like a 3 gigahertz clock speed or something. You know, on most chips. But you know, theoretically, right, two equal chips, if one's on a RISC style versus the x86, that one will generally kind of run a little faster. On the other hand, though, because we have fewer instructions for something like the LC3, we're going to require many more instructions to implement the same program than we would on the x86. The x86 is going to give us many more instructions that do very specific things. So the instruction count will be higher on a RISC-style computer like the LC3 than it would on the x86. So you can kind of see these two, these two different philosophies play out. The RISC-style computer is, generally less capable than a CISC-style computer. It has fewer instructions that do, fewer things. But that's going to make it easier to design. And I think you might be able to say easier to write simple programs on the LC3 because there's just a handful of instructions we have to understand. Harder to write more complex programs because we have to sort of combine instructions in maybe strange ways to do the things we want to. Whereas for a CISC computer, much more capable, many more instructions, many more different instructions, but definitely harder to design. And you might say the opposite, harder to write simple programs because there's a lot that I have to kind of hold in my head in terms of what these instructions are doing. Easier to write more complex programs because I have more tools at my disposal. Although these are kind of generalities a little bit, right? The two classic chip manufacturers that kind of supposedly occupy ends of this spectrum are ARM and Intel. So ARM is your classic RISC-style computer. Intel, that makes x86 chips, is your classic sort of CISC-style computer. But one thing I want you to take away from this discussion of RISC versus CISC, right, is that it's you might say a bit of a false dichotomy, right? It's useful to say certain things are sort of RISC style or CISC style, but there's hardly any computer that's pure RISC or pure CISC. In fact, if you look at some of the more modern chips that are being made from these two manufacturers, so the Cortex A15 is a chip that was released in 2010 from ARM. Sandy Bridge is one of the more recent Intel chips. You can read about both of these in our sort of supplementary textbook, Basic Computer Architecture. They kind of gravitate towards the center, and honestly, the more recent chips look much closer to each other than they do separately. So I don't want you to think that this is a computer is only ever RISC or CISC. It's sort of a spectrum, and things honestly the more recent designs kind of occupy a space close to the center with some RISC elements and some CISC elements. Okay, so to summarize, today we looked at the instruction set architecture for the LC3. We defined kind of what that is, that it's got these three components: instructions, registers, and memory. And we reiterated or expanded upon what these three elements are for the LC3. Predominantly, we took a look at 8 of our final 10 instructions in the LC3, which you can see here and which you're going to read about probably right after or maybe right before this video. And then along the way, we talked about the different addressing modes that are available to us in the LC3 and the difference between a RISC and a CISC style computer. Today's quote is brought to you by Fyodor Dostoevsky, who said, "There's only one thing I dread, not to be worthy of my sufferings." That's all I got. I'll see you next time.